'Cause nobody does it like you. I like the way that you move. That's why I never go through with leaving you.
Hi everyone, ready for some chemistry? In this video, I'm going to show you how to solve these problems. We'll go through the logic behind each answer, and I promise it's going to be quick and clear. Let's get started. Alright, moving on to question number 5. This one asks, which molecule has an equal number of bonding electron and lone pair electrons? Basically, we are looking for the molecule where the total number of electron in bonds match the total number of non-bonding electron perfectly. Which one do you think it did? Let's break it down. Before we start counting, let's quickly refresh the rules so we don't trip up. First, bonding electrons means the total count of individual electrons shared in bonds. So, for every single line or single bond, that's 2 electrons. Lone pair electrons means the total count of individual non-bonding electrons across the entire molecule. Our goal is to find where these two numbers are exactly the same. Let's check our options. First, let's look at option A, which is boron forms 3 single bonds here. So, its bonding electrons equal 3 times 2, giving us 6. But remember, boron is an exception to the octet rule here and has 0 lone pairs left over. Since 6 obviously doesn't equal 0, option A is a no-go. Next, let's check out option B. Carbon is in the middle with double bonds on both sides connect to the oxygens, giving us the structure O double bond C structure double bond O. That's 4 bonding lines total, which means we have 4 times 2 equals 8 bonding electrons. Now, for the lone pairs, each oxygen atom keeps 2 pairs of valency electrons to itself. That's 4 pairs total across the molecule, which giving us 8 lone pair electrons. Look at that, 8 equals 8, so we found our perfect match right here. Just to be absolutely sure, let's quickly cross-check option C. This molecule only has 2 single bonds, so it only has 4 bonding electrons. On the flip side, the fluorines and oxygens are packed with non-bonding electrons, totaling a massive 16 lone pair electrons. 4 versus 16 is definitely not equal, so C it's out. Finally, let's look at in option D. It has 3 bonding regions, giving us 6 bonding electrons. Meanwhile, if you count up all the individual lone pairs electron on the sulfur and oxygen, you get 10. 6 doesn't equal 10, so D is wrong too. That completely seals it. The correct answer is definitely B. Super straightforward once you count them out, right? Let's move on to the next one. Moving on to question number 6. The problem states methane and steam react to produce hydrogen. We are given the chemical equation and we have 0.80 grams of methane reacting with 1.35 grams of steam. We're told that one of the reactant is used up, and we need to find what volume of hydrogen gas will be produced at room condition. Let's solve this step by step. Step 1, let's write down and look at the balance equation. CH4 gas plus 2 moles of H2O gas yield CO2 gas plus 4 moles of H2 gas. Looking at the stoichiometry, this tells us that 1 mole of methane reacts completely with 2 moles of steam to produce exactly 4 moles of hydrogen gas. The smaller ratio is going to be crucial for our final calculation. Step 2. We need to find the initial moles of our reactant using their molar mass. For methane, the molar mass is 16 grams per mole. Dividing 0.80 grams by 16 gives us 0.05 moles of methane. For steam, the molar mass is 18 grams per mole. Dividing 1.35 grams by 18 gives us 0.075 moles of steam. Now, we have our starting amount in moles. Step 3, let's figure out which reactant limits the reaction based on our 1 to required ratio. If all 0.05 moles of methane reacted, we would need double that amount of steam, which is 0.10 moles. But looking back at our data, we only have 0.075 moles of steam available. Because we don't have enough steam to react with all the methane, steam is our limiting reactant and will be entirely used up. Step 4. We use our limiting reactant to calculate how much hydrogen is produced. From our balance equation, 2 moles of steam produce 4 moles of hydrogen gas, which simplifies to a 1:2 ratio. So, to find the mole of hydrogen, we take 4 over 2 and multiply it by our 0.075 moles of steam. This gives us exactly 0.15 moles of hydrogen gas. Step 5. Our final step is to convert those moles into gas volume at room temperature and pressure. Remember, at room condition, 1 mole of any gas occupies 24 decimeters cubed. So, we multiply our 0.15 moles of hydrogen by 24 decimeters cubed per mole. That gives us a final answer of 3.60 decimeters cubed. This perfectly matches option B. Great job! Let's keep going. Let's look question number 7. Here, we need to find the mass of a sample of methane using our favorite gas formula, PV equals nRT. We are given the temperature as 60 degrees Celsius, pressure as 103 kilopascals, and the volume as 5.37 times 10 to the minus 3 meters cubed. Let's break this down and solve it. Step 1. We need to make sure all our units match standard SI units so the formula works perfectly. For pressure, 103 kilopascals become 103 times 10 to the power of 3 pascals. Our volume is already good to go in meters cubed. For temperature, we can't use Celsius, so we add 273 to 60, giving us 333 Kelvin. And of course, our gas constant R is 8.31. Step 2. Let's rearrange the equation to solve 4 moles. That gives us N equals PV over RT. When we plug in our numbers, the top half equals 553.11 and the bottom half equals 2767.23. Divide those two numbers and we get approximately 0.1998 moles of methane. Step 3. Now that we have the moles, we can easily convert them into mass. The molar mass of methane CH4 is 12 for carbon plus 4 times 1 for hydrogen, which gives us 16 grams per mole. Multiplying our 0.1998 moles by 16 grams per mole leaves us with roughly 3.197 grams. Step 4. Our final step. The question specifically asks for the answer to 2 significant figures. So, rounding 3.197 grams to just 2 significant figures gives us exactly 3.2 grams. This matches option D perfectly. Always watch out for the specific requirement at the end. Guys, let's move on to the next questions. Now let's look at the question number 10. This is about the different structures of an element. We are given 3 structures, P, Q, and R, which represent graphite like diamonds, and fluorines like structures. The questions ask, which structures are giant molecular? Let's break it down step by step. First, let's understand the definition in chemistry. In structure of elements are generally divided into 2 main categories based on how they bond. Number 1, giant molecular or giant covalent structures. These are boundless network of atoms held together by strong covalent bond extending through the entire substance. And number 2, simple molecular structure. This exists as distinct isolated molecules, while the atom inside the molecules have strong covalent bonds. The molecules themselves are only held together by weak intermolecular force. Now let's analyze each structure. Look at structure P, which is like a layered hexagonal network, like graphite. Here, each atom forms strong covalent bonds with 3 neighboring atoms, creating continuous infinite 2D sheet layer on top of each other. Because this network extends infinitely, it is classified as a giant molecular structure. Next, it's structure Q, a 3-dimensional tetrahedral network. Like diamond, each atom forms 4 strong covalent bonds in a vast 3D grid. Since it forms an uninterrupted infinite lattice, it is also classified as a giant molecular structure. Finally, let's look at structure R, which is spherical cage structure like fluorines. Here, atoms bond together to form close soccer ball-like spheres, such as C60. Even though the individual catch has strong internal bond, it exists as a discrete, isolate molecule because it has a fixed molecular formula and the molecules interact via weak van der Waals force. It is classified as an simple molecular structure. Therefore, only P and Q are giant molecular structure. Looking back at our option, the correct answer is B, P and Q only. Moving on to the next question, number 11 asks us about the shape of a sulfur dioxide molecule. The problem shows a basic structural layout of SO2 and mentions there are lone pairs of the atom. We need to find out whether its molecular shape is linear, nonlinear, pyramidal, or tetrahedral. Let's break it down. Step 1 is to analyze our central sulfur atom. To find the geometry of sulfur dioxide, we need to look at its valence shell. Sulfur is in group 16, so it has 6 valence electrons. In the structure, sulfur forms 2 double bonds, which the oxygen atoms just use up 4 valence electrons, 2 for each double bond. If we subtract those 4 from the original 6, we have 2 electrons left over, which give us exactly 1 lone pair of the sulfur atom. In step 2, we determine the electron pair geometry using VSEPR theory. Remember, for molecular geometry, a double bond is treated as a single bonding region or electron domain. So we have 2 bonding regions from the double bonds, plus 1 lone pair of the sulfur. That gives us a total of 3 electron domain, or a steric number of 3 to minimize repulsion. The atom arrange these 3 domains in a trigonal planar orientation, about 120 degrees apart. Finally, step 3 gives us the actual molecular shape, while the overall electron geometry is trigonal planar. The molecular shape only looks at the position of the atoms, ignoring the invisible lone pair. That lone pair on top exerts a strong repulsive force, pushing the 2 sulfur oxygen bonds downward. The distortion bends the molecule out of a straight line, which in chemistry nomenclature we call nonlinear. Therefore, the correct answer is B, nonlinear. Next up, it's question 12. This one is a bit of a puzzle. We have to find which pair of molecules has the exact same shape. We have 4 options, A, B, C, and D. To solve this, we can just guess. We have to look at the structure atom itself. Let's dive in. To find the answer, we use a simple key called the steric number. It's basically just adding up the number of atoms attached to the center plus the number of lone pairs. If 2 molecules have the same number of bonds and the same number of lone pairs, they'll have the same shape. Let's test our option. Let's check option A, water and carbon dioxide. We already know water is bent because it has 2 lone pairs, but carbon dioxide, it has 2 double bonds and 0 lone pairs, making it a perfectly straight line or linear. Since one is bent and the other one is linear, option A is a no-go. Now, for option B, water and sulfur dichloride. We know water is bent. Now look at sulfur dichloride. Sulfur is in group 16, just like oxygen, so it also has 6 valence electrons. It used for 2 bondings and keeps us 4 as 2 lone pair. This is a perfect match. Both molecules have 2 bonds and 2 lone pairs, meaning they are both bent. We found our answer. Alright, let's move on to the question number 13. We have a sample of magnesium containing 3 isotopes, magnesium 24, 25, and 26. We are told that the percentage abundance of magnesium 25 and 26 is exactly the same, and the overall relative atomic mass of the sample is 24.3. Our goal is to find the percentage abundance of magnesium 24. Step 1. Let's define our variables to make the math easier to handle. We will let the abundance of magnesium 24 be X%. Since the problem states that the abundance of magnesium 25 and 26 are equal, we can represent both of them using the same variable, Y%. Remember that the total percentage of all isotopes combined must always equals 100%. So x plus y plus y equals 100. This simplifies to x plus 2y equals 100. If we rearrange this to solve for y, we get y equals 100 minus x all divided by 2. Step 3. Now we set up our relative atomic mass formula. The average atomic mass is calculated by multiplying each isotope's mass by its abundance, adding them up and dividing by 100. Substituting our values gives us 24.3 equals 24x plus 25y plus 26y over 100. To clear the fraction, we multiply both sides by 100, which simplifies nicely to 2430 equals 24x plus 51y. Step 4. It's time to substitute our expression for y into this new equation. We replace y with 100 minus x over 2. To easily get rid of the denominator, let's multiply the entire equation by 2. This leaves us with 4860 equals 48x plus 51 times the quantity 100 minus x. Finally, let's expand the brackets and combine like terms. This gives us 4860 equals 5100 minus 3x. Rearranging the equation to solve for x, we find that 3x is equal to 140. Divide both sides by 3 and we got the x equal 80. Therefore, the percentage abundance of magnesium 24 is 80%, making option D our correct answer. Moving on to question number 14. Here we are looking at how ammonia reacts with acids to form the ammonium ion. We need to figure out which row correctly identifies both the molecular shape and the bond angles of this ammonium ion. Step 1. Let's understand how the ammonium ion is formed. A neutral ammonia molecule reacts with hydrogen ion. Now, the central nitrogen atom in ammonia has 5 valence electrons. It shares 3 of them with hydrogen atoms, leave behind 1 lone pair nitrogen, then donates this entire lone pair to the electron deficient H ion, forming what we call a dative covalent bond. Step 2. Let's count the electron domains around the central nitrogen atom after the bond is made. We now have 4 bonding regions because of the 4 nitrogens to hydrogen single bonds. Since that original lone pair is now being shared to form a bond, we are left with 0 lone pairs. This gives us a total of 4 electron domains. Step 3. Let's determine the final shape and bond angle using Evans EPR theory, with 4 electron domains and 0 lone pair pushing them out of character. The molecular geometry becomes a perfectly tetrahedral. A regular tetrahedral shape always exhibits an ideal bond angle of exactly 109.5. Therefore, looking back at our option, row D is the correct match. Let's move on to the question number 16. We have an energetic experiment here where 25 cubic centimeters of hydrochloric acid is mixed with an equal volume of sodium hydroxide. The temperatures rise from 15 degrees Celsius up to a maximum of 30 degrees. Our task is to calculate the enthalpy change of neutralization for this reaction. Step 1. Let's calculate the total heat energy release using our trusty formula Q equals to mc delta T first. We find the total mass by adding the volumes of both solutions together, giving us 50 cubic centimeters, which convert to 50 grams based on the density. Next, we find the temperature change, which is a jump of 15 Kelvin. Plugging everything in, we get a total heat release of 3,135 joules or 3.135 kilojoules. Step 2. We need to find out how many moles of water were actually formed. Since the enthalpy of neutralization is defined per mole of water by using our moles formula, concentration times volume in cubic decimeter, we find that we have exactly 0.100 moles of hydrogen ions and the same amount of hydroxide ions. Since they react in a perfect 1-to-1 ratio, exactly 0.100 moles of water are produced. Step 3. Now we can find the final enthalpy change of neutralization. We divide the heat released by the moles of water formed. Because the temperature increase, we know this reaction is exothermic, so we must add a negative sign to our final value. 3.135 kilojoules divided by 0.100 moles gives us minus 31.35. Rounding to 3 sigfic, we get minus 31.4 kilojoules per mole. That makes option B our correct answer. Let's move on to question number 17. We are looking at an experiment to find the standard enthalpy change of combustion of ethane. We're giving the standard combustion values for carbon and hydrogen as well as the standard enthalpy change of formation for ethane, which is minus 140 kilojoules per mole. Our task is to calculate the experimental value for the combustion of ethane. Step 1. Let's define our chemical equations to solve this problem using Hess law. We first look at the standard enthalpy change of formation for ethane. The balanced chemical equation for forming 1 mole of ethane gas from its constituent elements in their standard state is 2 moles of solid carbon plus 3 moles of hydrogen gas react to form 1 mole of ethane gas. The enthalpy change for this step is given as minus 140 kilojoules per mole. Step 2, we need to construct a Hess-Lowe cycle. We can link the reactant and product of our formation reaction to their respective combustion products, which are carbon dioxide and water. According to Hess-Lowe, the total enthalpy change of a direct route equals the total enthalpy change of an indirect route. Rearranging this formula to isolate our target value gives us the enthalpy of combustion of ethane equals the sum of the combustion enthalpies of the reactants minus the enthalpy of formation of ethane. Step 3, let's calculate the total heat energy released by burning the elements on the reactant side. We have 2 moles of carbon and 3 moles of hydrogen gas, so we multiply 2 by minus 394 and add 3 times minus 286. This gives us minus 780 plus minus 858. Resulting in a total reactant combustion enthalpy of minus 1646 kJ per mole. Step 4, now we just substitute these values back into our rearranged Hess-Lowe equation to solve for the combustion of ethane. We take our reactant total of minus 1646 and subtract the formation values of minus 140. The two minus signs turn into a plus, giving us a minus 1646 plus 140. This leaves us with a final answer of minus 1506 kilojoules per mole, which perfectly match option B. Next is question 19. As you can see from the picture, it's asking about the standard enthalpy change of combustion of carbon. For the step 1, you guys have to write the formation equation for ethane. The standard enthalpy change of formation is defined by the reaction creating 1 mole of ethane from its constituent element standard states. And step 2, it's establish the Hess-Lowe cycle relation. You guys have to using standard enthalpy change of combustion. The relationship can be modeled by a standard thermodynamic cycle. The formula already shown in the picture. Breaking this down specifically for our reaction. And then step 3, you guys have to set up the equation with known variables. Let x represent the incorrect value used by the student for the combustion of carbon. So we plug in the final answer, and the correct value used that the student used is that the enthalpy change of formation is calculated equals to minus 158 kilojoule mole, the power of minus 1. And the enthalpy change of combustion hydrogen, it's equals to minus 286 kilojoule mole, the power of minus 1. And then the last one is the enthalpy change of combustion ethane, it's equals to negative 1060 kilojoule mole, the power of minus 1. And for the last step, you guys just have to solve the algebraically for x. The first one, you guys have to simplify the numbers step by step like this picture. And then I got negative 430 kilojoule mole per 1, so the correct answer is C. Next is question number 20. The question asking about the which expression gives the standard enthalpy change of formation of methanol in kilojoule mole, the power of minus 1. So step 1, you guys just have to define the chemical equation. To solve this using Hess-Lowe, we look at the standard enthalpy change of formation for ethane. And then step 2, you guys have to construct the Hess-Lowe cycle. We can link the reactant and product of the formation reaction to their combustion products to create an enthalpy cycle. And step 3, you guys just have to calculate the total combustion of reactant. Calculate the energy released by burning the element on the reactant sides, 2 moles of carbon and 3 moles of hydrogen gas. And then step 4, you guys just have to solve for the combustion of ethane. And you guys just have to substitute the value back into our rearranged Hess-Lowe. And then I got negative 1506 kilojoule mole, the power of minus 1. Next, it's question number 21. Ethane or C2H2 completely combusts based on the equation. Using the bond enthalpies in the table, let's find the total enthalpy change of combustion. Let's break it down. Step 1. Count the bonds. To find delta H, we use bond broken minus bond form. Delta H equal bonds broken minus bond forms. In the reactant, we break 2 CH bond, 1 C triple bond C, and 2.5 O bond. In the products, we form 2 OH bond and 4 COO bond. Step 2. Here are the values from the table. CH is 410, C triple C is 840, O is 496, and OH is 460, and COO is 740. Step 3. Calculate the total energy. Total bonds broken equals 2 times 410 plus 84 plus 2.5 times 496, which totals 2900 kilojoules. Total bonds formed equals 2 times 460 plus 4 times 740, which totals 3880 kilojoules. Step 4. Now just subtract them. Delta H equals 2900 minus 3880. Delta H equals 2900 minus 3880. The final answer is minus 980 kilojoules per mole. That matches with option A. Next is question number 22. We're converting compound X into Z through a stable intermediate Y. Let's find out which reaction profile fits the data. Let's check the mechanism. Step 1. Analyze the steps. The reaction goes from X to Y, then Y to Z. Since compound Y can be isolated, it is a stable intermediate. In an energy profile, an isolable intermediate is always represented as a value between two peaks. Step 2. Look at the enthalpy change. The first step, X to Y, has a positive delta H, meaning it's endothermic, so Y sits higher than X. The second step, Y to Z, has a negative delta H, meaning it's exothermic, so Z sits lower than Y. Step 3. Match the profiles. Profiles are matched perfectly. Energy rise from X to a peak drops to a valley at Y, where Y is greater than X. Rise to a second peak and drop significantly to Z, where Z is less than X. The correct answer is profile A. So moving on to question 25. We are given the enthalpy change of neutralization for a strong acid and a strong base. Based on this information, we need to find the enthalpy change for a second reaction. Let's look at the rules. Step 1. Understand the definition of enthalpy of neutralization. So, the standard enthalpy change of neutralization is defined for the formation of 1 mole of liquid water for any strong acid reacting with any strong base. The essential ionic equation is always identical. H plus aqueous plus OH minus aqueous react to form H2O liquid with a delta H of approximately minus 57 kilojoules per mole. H plus aqueous plus OH minus aqueous goes to H2O liquid delta H equals minus 57. 2NiOH plus H2SO4 reacts to form Na2SO4 plus 2H2O. 2NaOH plus H2SO4 goes to Na2SO4 plus 2H2O. Both are strong electrolytes, and this balance equation forms exactly 2 moles of water. Therefore, the heat release is double. Minus 57 times equals 2 equals minus 114 kilojoules per mole. Minus 57 times 2 equals minus 114. Step 3. Now look at our target equation. BaOH 2 plus 2HCl react to form BaCl 2 plus 2H2. BaOH 2 plus 2HCl goes to BaCl 2 plus 2H2O. Barium hydroxide is strong base and hydrochloric acid is a strong acid. Just like the first reaction, this equation also forms exactly 2 moles of water. Step 4. Compare and conclude. Since both reactions involve fully ionized strong acids and strong base, and both produce exactly 2 moles of water, the net energy release will be identical. So, delta H is also minus 114 kilojoules per mole. So, the correct answer is C. Next is number 27. In this question, it's asking about the enthalpy change of the process shown in equation 1. So the step 1, it's you guys have to find the enthalpy change for the overall target process. You guys have to manipulate and combine the 3 given substages so that when they are added together, they perfectly yield our target equation. And then step 2, you guys have to manipulate the substage. And then you guys have to modify stage 2. And after that, in the step 3, you guys have to sum the equation using the Hess law verification. And step 4, you guys have to calculate the total enthalpy change. And then we got the answer is negative 370. So the correct answer is B. Next, it's question 31. In which direction is the underlying substance acting as a base? Note the underlying substance is listed first in each option below. Okay, so step 1, you guys have to understand the Bronsted-Lowry theory first. And then in step 2, you guys have to analyze each option. And then this is the summary table. And then for the number 32, it's asking about the which mixture results in a solution with the highest pH. So the step 1, you guys have to understand the trend of period 3 elements with water. And then you guys have to analyze each option. And after that, you guys will get the results. It's like this summary. And then we get the answer, it's B. And then next, it's question number 33. It's asking about the which mixture will react to form exactly 1 mole of water. First, you guys have to write the balanced chemical equation. And then step 2, you guys have to calculate the moles for B option. And then you're gonna get your answer. And next is number 34. It's asking about which row gives the identity of P and Q. Step 1, you guys have to analyze the pH jump. And step 2, you guys have to analyze the reaction stoichiometry. And then we get the right answer, it's option C. And then next, it was question 39. In which reaction is the underlying substance acting as a base? So step 1, you guys have to understand the Bronsted theory. And then step 2, you guys have to analyze each option. And then after you guys analyze your option, you're gonna get this summary. And if we get the answer, it's C. So in the first question, part A, asks us to determine the charge on the electric plates based on how electron and proton beams deflect and to predict the path of the neutron beam. And part B, it asks us to calculate the number of occupied sp and the orbitals in a krypton atom. Let's break it down step by step. Let's look at the part A1. Opposite charge attract while like charge repel. Left plate, the electron beam bends to the left since electrons are negatively charged. They are attracted to the positive plate. Right plate, the proton beam bends to the right. Since protons are positively charged, they are attracted to the negative plate. Now for part A2, how do neutrons behave? Neutrons are neutral. They carry absolutely no electrical charge. Because of this, they experience no attraction or repulsion from either plate. As a result, the neutron beam travels completely straight right through the middle, entirely undeflected. Finally, let's solve part B1. For krypton, which has 36 electrons, its full electron configuration, it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. Let's count the occupied orbitals by type. S orbitals, we have 1s, 2s, 3s, and 4s. Each subcell has one orbital, giving us a total of 4. P orbital, we have 2p, 3p, and 4p. Each subshells contain 3 orbitals, so 3 times 3 is equals to 9. D orbitals, we only have the 3d subcells, which contains 5 orbitals. So we just gonna fill in the table with 4, 9, and 5, and it's our final answer. Moving on to the next part of the question, in part 2, we need to complete an orbital energy diagram for an isolated silicon atom, which has 14 electrons in part 3. We are shown a specific orbital shape and asked to find the total number of electrons that occupy this type of orbital in a fluorine atom. Let's look at how to fill this in. Let's complete the diagram for silicon with 14 electrons. We followed the Aufbau principle, Hund's rule, and the Pauli exclusion principle to fill the subshell from lowest to highest energy. 1s, 2s, and 3s each gets a pair of opposite arrows. Note that 1s is already done for you. And 2p, the subshells, is fully filled, so we place a pair of opposite arrows in all 3 boxes. 3p, according to Hund's rule, electrons occupy empty orbitals singly, first with parallel spins. So, we place one single upward arrow in the first box and one single upward arrow in the second box, leaving the third box empty. 4s is remain completely empty. Finally, let's look at part 3. The dumb shell shape shown in the diagram represents a p-type orbital. To find the answer for a fluorine atom which has 9 electrons, we write out its electron configuration: 1s2, 2s2, 2p5. By looking closely at the subshells, we can see that there are exactly 5 electrons occupying the p-type orbitals, allocated within the 2p subshell. Simply write down 5 on the line to complete the answer. Let's look at the question 1a regarding stable isotopes of chromium. For part 1, we located chromium on the periodic table to find its atomic number, which is 24. This means a neutral atom has exactly 24 protons and 24 electrons. To find the number of neutrons, we subtract the atomic number from the mass number 52 minus 24, giving us 28 neutrons. For part 2, we need to explain how chromium-54 differs from chromium-52. Isotopes of the same element always share the exact same number of protons and electrons, but differ in their mass because of their neutron count. Subtracting the atomic number from the new mass number, 54 minus 24, gives us 30 neutrons. Therefore, an atom of chromium-54 has exactly 2 more neutrons than an atom of chromium-52. Now for part B1, we are given the shorthand configuration of chromium as Ar3d5 4s1, and the symbol argon represents the noble gas of core of argon, which accounts for the first 18 electrons. To write out the full configuration, we expand that core into its complete subshell sequence. Write down 1s2, 2s2, 2p6, 3s2, 3p6 right on the line before 3d5, 4s1. For part B2, we need to find the total number of unpaired electrons in a chromium atom. All inner subshells from 1s to 3p are completely filled and paired up. We look only at the outer 3d, 5 and 4s1 subshells. According to Hund's rule, the electrons occupy empty orbital slightly first. The 3d subshell has 5 orbitals with 5 single electrons, and the 4s subshell has 1 orbital with 1 single electron. Adding them together gives a total of 6 unpaired electrons. Let's move on to question 1b regarding magnesium isotopes. Part 1 asks for the definition of relative isotopic mass. The precise definition to write down is the mass of an atom of an isotope compared to 1 per 12 of the mass of an atom of carbon 12. And for the second part, we need to calculate both the percentage abundance and the isotopic mass of magnesium third isotopes. Let's find the first abundance first. The total percentage abundance of all natural isotopes must equal to 100%. We are given at the first two abundance as 79% and 11%. Subtracting this from 100% give us 100% minus 90%, leaving exactly 10% for the third isotope. Now let's calculate the isotopic mass of that third isotope, which we will call X. We use the relative atomic mass formula 24.3 equals to 100. So 24 times 79 plus 26 times 11 plus X times 10. So multiplying by 100 simplifies the equations to 2430 equals to 1896 plus 286 plus 10x. Combining the constants gives 2430 equals to 2182 plus 10x. Isolating the variable gives 10x equals to 248, which means x equal to 24.8. So our final answer is 236 Vic are 10% and 24.8. So for the next question, it's the symbol argon. It represents the noble gas core of argon, which has an atomic number of 18. You just need to write out the subshell configuration for those first 18 electrons. And then for the second one, it's all s orbitals, regardless on their principal quantum number, and share the exact same geometric shape. Shape description is spherical. And then the given shorthand configuration, it's argon 3d7 and 4s2. To find the unpaired count, look only at the incomplete outer subshells. So first, it's 4s2 subshells has one orbital containing 2 electrons. They are completely paired up. And then 3d7, its subshells has 5 degenerated d orbitals. So following controls, we distribute the 7 electrons into the 5 orbital one by one before pairing them up. So first, place the 1 electron in each of the 5 orbital, all pointing up. This use 5 electrons. And then the second, pair up the remaining 2 electrons into the first 2 orbitals pointing down. This leaves the final 3 orbitals with only a single unpaired electron each. So total unpaired is 3. And then the next question is to complete this table cleanly on your blackboard. We decode each row using standard isotopic notation, where A is the mass numbers and Z is the atomic number. And to complete this table cleanly on your blackboard, we decode each row using standard isotopic notation, and where A is the mass number and then the Z is the atomic number. So the number of proton is 45, and then the number of electron is 5. And then number of n elements always equals its total number of occupied principal electron shells. And then it's same with the row 2, and then also it's same with the row 3. And after that, let's move on to the next question. In this question, you guys have to determine the total percentage of iridium in the alloy. And then you guys have to set up the weight average equations. And then the step 3, you guys have to solve the numerators. And then the step 4, you guys have to round to 2 decimal places. And then you guys have the answer. And then next, it's you guys have to divide the relative atomic mass. And after that, for the calculation, you guys have to calculate the percentage abundance of third isotope first, and then set up the weight average equation, and then solve for the x. And then you guys gonna have the answer like shown in the picture. And then this one about the number of pair of electrons, it's 1. And then we have to identification about the shape, it's spherical. And then this is the next questions. The answer are already right. And then to write the standard enthalpy change of formation equation, you must form exactly 1 mole of the product from its pure element in their natural physical states at 298 K. And then you guys have to use the Hess formula. And then after that, step 1, you guys have to sum of product and then sum of reactant, and then you guys have to subtract reactant from products, and then you guys gonna get the answer. And after that, this question you guys have to complete like I already draw. And then after that, we have to determine the electron pair geometry, and then deduce molecular geometry, and then determine bond angle. And then for the last questions, you guys have to calculating, and then of course you guys have to standard the balance equation first. And after that, you guys have to use the Hess formula. And then for the calculation, you guys have to sum of the product and then sum of reactant, and then subtract the reactant from product, and then you guys gonna get the answer.